In this problem, we have an amusement park type situation where we have a track, or what the problem calls it a boom, but if you don't know what a boom is like a long metal beam. And if you've ever been to an amusement park, it's the kind of track that the roller coasters are on. That's what a boom is. And it's saying we have a case where we have a loop of a boom, and there's a car going around it, and at the point where the car is on top, we're given its speed, its tangential speed, and we want to find out what the force is on the car from the boom. So if we were to draw a little free body diagram here, we know what its weight is going to be. It's going to be a downwards force, and we're told what the weight is. It's going to be 5.0 kilonewtons, or 5,000 newtons. I'm just going to write that as the weight of the car. But what's interesting about this problem is that we don't actually know what the direction is of the force on the boom. It could be up, it could be down, depending on various factors, depending on what the speed of the car is. Because if the car is going like really fast, then the force from the boom will probably be like a downward force, because it's pulling the car down so it doesn't fly away. But if it's a lower speed, then the car is probably weighing down more heavily on the boom, so it'll probably be more of an upward force. So how do we represent this in a free body diagram? Well, the way I'm going to reconcile this, the way I'm going to handle this is, I am going to define a coordinate system so that up is positive. And by definition, that means that down is going to be negative. And I'm going to say that the force from the boom on the car is going to be positive upwards, along that positive direction. And the reason why I'm doing it this way, it's technically arbitrary, you could do it either way, but I think this way is going to be slightly simpler, because when we find a formula, when we derive a formula for the force from the boom, if this value, f sub b, turns out to be positive, then we know it is an upward force. But if it turns out to be negative, then we'll see that's actually a downward force, pointing downwards. So this is what we're going to work with. We're going to start with positive. We're going to start with an upward force on our free body diagram, and if the force turns out to be negative, then it's actually a downward force. So now let's use Newton's second law. The net force on an object is equal to ma. It's not at rest here, so we're not going to set it equal to 0 like we sometimes do in other problems. There's going to be a centripetal acceleration here. And actually, because that acceleration is centripetal, I'll just plug in the formula for that right now. It's going to be m times the centripetal acceleration, which is equal to the speed squared, v squared, divided by r, where r is the radius of the loop, of the circle. And the centripetal acceleration is always directed towards the center of the circle, inwards. And because of that, we can see from the system I set up that it's going to be negative, which means that this term here should be negative because the centripetal acceleration is negative. So this is a negative mv squared over r term on the right. Now as for the left term, the other forces we've got here, so as we talked about before, there is an upwards f sub b, or it could be upwards, who knows, and then it's countered by a downwards force from weight. So we want to rewrite this equation to solve for f sub b. So to do that, I'm just going to say that f sub b is equal to, and then I'm going to put a positive weight term here, because I'm going to add both sides, add w to both sides of this equation. They get f sub b on its own. So it's equal to w minus mv squared over r. This is a pretty good equation. We're given the weight, except we don't have the mass of the car. That's not something the problem gives to us. But fortunately, it's not that hard to figure out what the mass of the car should be, because weight, by definition, is equal to the mass times g, the acceleration due to gravity. So one way we can rectify this is to solve this formula for m, and we can see that the mass is going to be equal to the weight divided by g, divided by that acceleration due to gravity. So we can just plug that into our equation. So it's equal to weight minus, and then for m I'll just write the weight, the w over g, and then multiply that by v squared over r. So now everything in this equation is known, given to us by the problem, and for g we'll just use 9.8 meters per second squared. So if we put this into our calculator, then we find that the force F sub b is equal to about 3.7 times 10 to the power of 3 newtons. So that is the magnitude of the force, and what you'll notice when you put this into your calculator is that it is positive. This answer is not negative, which means that the direction of FB is in fact upwards. So I'll make note of that too. It's an upward direction. We had that little guess we made right. But now let's look at parts C and D, where now the speed has been increased to 12 meters per second. So we can just do the exact same thing. I'm going to label this as part C first. So we can use this exact same equation that we found above. We'll use the same equation, the weight minus all of this, minus the weight over g times v squared over r, except now we're going to use 12 meters per second for v, yeah. And this time we find that the force F sub b is equal to negative 2.3 times 10 to the power of 3 newtons. Now, if the problem asks for magnitude, we can just disregard the negative sign. But the negative sign is still very useful because it tells us that it's directed downwards. This is going to be a downward force because the fact that it's a negative sign indicates that this force is going to point along the downward, the negative direction of the axis of the coordinate system we set up. So that is what we're going to use here. That is our answer. I will add that because this coordinate system was something that we came up with, it might technically be considered improper to write your final answer to part C here with this negative sign, because the negative sign isn't like intrinsic to the problem or anything. That was based on a coordinate system we came up with. So if you're like filling out these answers online, or if you're writing an answer kind of to a problem like this to your teacher, you might not want to include the negative sign and just add that it's a downward force, but I suppose that just depends on how the teacher is giving this problem. But either way though, that's the gist of this problem. That's how you do this problem. And that's all for the solution. I hope this video helped you out. If it did, please consider subscribing, as that'll help me make more videos like this. And if you have any questions, leave a comment down below and I'll do my best to help you out. But that's all for now, and I hope you all have a lovely day. Bye-bye.